Yes, good morning, everyone. This is the second day of my this module three, this subsystem design process. I hope I'll just run through the previous class data. This is subsystem design process where certain system will be there. We need to partition that system, or we need to divide our system into subsystems because you cannot directly build one complete system. So we'll be taking each module. We'll work on module or subsystem. So we'll verify the functionality. If everything is proper, then we'll go for other system. Again, you design that, then try to interconnect these two subsystems. How many, based on the requirement, you divide into different subsystem. Each one individually you need to check, then you interconnect it. Once everything is done, then only you'll get complete system. That's what this is the requirement of subsystem. You cannot easily build the system directly. So that's why you need to divide your system into subsystem, work on each subsystem, then you interconnect and make sure all subsystem will work properly. uh, in our module, we have this 4-bit microprocessor. This one processor is the system, and that system we have different modules. The subsystems, so the ALU will be there, control unit there, IO unit will be there, memory, all those things we'll be dealing with in our topic. That's what we have learned in the previous class, and these are the general consideration. When you're building your system, you need to make sure it will have low unit cost. Obviously cost should be very less, and higher reliability. Obviously your system should work for 1 or 2 years. You should not be like after 6 months every time you'll be changing your new system. Low power dissipation, obviously it should last more. When you take your mobile phone, at least minimum 1 day should come. Obviously you don't want your phone to be recharged every one now and then. Obviously lighter weight, so you should be in a position to carry that in your pocket. Obviously performance, then enhanced repeatability. So repeatability means like when you build your system, if you build your working module or working system, that system you can repeat it. If like Android 9, you see how many Android 9 version will be there. Like Android 9 you can fit in different platforms. Same way, when you build system, you should be in a position to replicate those things. Obviously reduce design and development periods. You should when you're getting new product into market, that development period should be less. Within 4 months or 3 months, you should be in a position to launch your product. If you're not launching your particular product, no other competitor will come and they'll take over the entire market. That's why you see, whenever Apple is launching new product, there'll be obviously some competitor will be there in terms of Google, or UI, or some other company. Similar features will be there. They will also try to launch. If you're not launching that particular product in that particular time, so some other company will take over your entire business. And this is the general 4-bit arithmetic processor. So we have seen this. There'll be a control unit will be there. Then ALU will be there, memory unit, IO units, all those things will be there. That's what we have seen. No, this each one is one submodule. Each one is one submodule. Control unit is one submodule. ALU will be one submodule. Memory unit is one submodule. IO units, all those things are different submodules. And based on the control circuitry, you can take the data. You'll go to particular address, take the data, that data through database, and store it in your memory, or do some computation in ALU, store it in memory, or you display it in your output terminal or something like that. You can do it. Then we have seen different bus architectures. One bus architecture where for all the operation, one bus will be there. You see this, this is a register or memory element. Take During first clock cycle, you take this first operand from the memory to ALU, then store it in certain register. Then again take the second data, again put it in ALU, do some computation in ALU. It can be a addition, subtraction. So that result again you will be sending to shifter. So you require 3 clock cycle to no actually compute the data and again store it in register. That is that's the problem with your one bus architecture. Again, you can perform. Only thing is it will be a little slow. In two bus architecture, two buses will be there. So this is a bus or 4-bit bus, no? Then this is second bus. So parallelly, you take the data from this register, put it onto your ALU, compute the data using the shifter again. You can send back or shift the data back to your register. So here you require only 2 clock cycles. Sorry, listening. Again in 3 bus architecture, uh, like 3 different buses will be there. Like this is one bus. This this is one bus. This is second bus. This is third bus. So parallelly, you'll take this data. A, B will be loaded parallelly. Computation will be done, and even the shifting will be done through this third bus parallelly. It's like there'll be inherent delay, or the default delay will be there. That delay will be very less. So that's why if you see this, so it takes only 1 clock cycles to compute all your operation. See, you take this, see, both operands A and B are sent from register operated in ALU on the results which is shifted returned to other registers. All this happen in same clock period. So within 1 clock period, so taking the data from different registers to ALU, computing that result, then shifting the data through. Hello, some network issue is there. So again, I'm back online. Um, this is a 4-bit shifter. I told you here, you see, every bus architecture we have the shifter. Is dealing with the shifter which shifts the data based on the number of clock cycles. You can shift either to the right or to the left. So 4-bit data you can shift at a time. Either you can shift left or shift to right. So under that, this is the first one is 4x4 crossbar switch. So 4x4 crossbar switch. It's like 4 inputs and 4 outputs are there. That's why it's called 4x4 crossbar switch. Many times they've asked this. In this 4x4 switch, so at a time you need to activate 4 switches so that data will be shifted. So if I take this, so this is one data. So I need to turn on this, 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 this. If I take this, so automatically data will be shifted. So I'm taking this one switch to the second switch to the third switch, and this is fourth switch. If I use this, I go for the other one. So yeah, so I'll turn on this switch, this, and this. If I turn on these switches, so data will be moved in this way. I in one will move from year to year. So out will be this. Then I in two will go to out one. Then I in three will go to out two. So and I in zero will go from year to year. That is I not three, out three. So this way will be shifting our data. you can see at a time I need to take 4 switches. I need to turn on 4 switches so that I can shift data towards right or left. So this is the drawback is like you require 4 switches at a time. At a time you need to select 4 switches. Based on that, you'll be sending the data. So we can avoid this drawback using a barrel shifter. In a barrel shifter, again it's a 4x4 barrel shifter. So this is the barrel shifter. You can see this here. No, all the 4 transistors are shorted. This is also 4x4 only. Only difference is here the data is the transistors are shorted. You can see this. This is one transistor, second transistor, third transistor, and the fourth transistor. All 4 transistors shorted. The moment I turn on this S0, the moment I turn on this S0, automatically this I0, which is shorted, it will go from here to Q0. Same way I1. I1, different color. This is I1. I1 will go from here till here. Then I2. I2 also will be moving from here. So this is the path it will be taken. Then I3. This I3 will go this way. So when the moment you turn on this S0, all 4 transistors will be turned on and data will be shifted towards your right. Same way you can do another way. See this. You see these things, S1 is shorted here. S1 is shorted from here to here. These 2 transistors are shorted. Again, this is going this way. Is going this way. So this way, you can short your data and you can send. That's what is happening. So you can see table also. So this is the table. When S1 is 1, and you will get this output I0, I1, I2, I3. Then when S1 is turned on, that means these transistors turned on, data will be moving in this way. So you can control your movement of data from year to year. And this is one more circuit where in which this is also similar to this barrel shifter only. Here it looks a little cumbersome, not because we don't know which metal layer you're using, where you're connecting. If I use same metal one, so there'll be a short. You cannot write this circuit because if you're using different color pattern, then you can use, because polysilicon metal, you see, no, there is no much difference. But when you see this actual circuit, this is from textbook, uh, not from your Pucknell. This is from the internet source I have taken. If you take this one, you see, little shaded one is there. This one, you can see this polysilicon is different color, and this is metal. Horizontal is metal. You can take this way. You can see this. This is A naught is there. This is A naught. This is a metal, and this is also connected to metal. This is metal. This is not there. This eraser. You need to understand this carefully. And this is the transistor. If I turn on this SH naught, you see this A naught will go to this transistor. And again, you see, this is a different color combination. This will go to V naught. Able to follow? You see, this polysilicon is different color. I've used the same color, but you can take in this way. Polysilicon is this. So this is your polysilicon, which is different color from your actual metal. So that way you can avoid. If you want to use different color, if you're using different color, then well and good, no, you can go ahead with the circuit. But if you're using same color, you need to make sure, no, for metal and polysilicon you'll be using different color. You can see, bold and little shade is there. So that's where, no, you can differentiate your metal and polysilicon. So this is what we have discussed in previous class. Then there are one more subsystem is ALU. ALU, again, this is how it works. ALU, the major one of the major component of ALU is your full adder. Full adder. So here what we are doing is, now we are building full adder using mux. Implementation of your full adder using mux. Here, three input combinations. So they have taken different terminology, that is AK, VK, CK, and sum is your SK and carry out is CK. You need to see this. CK minus 1 is your carry in and CK is your carry out. CK minus 1 is carry in and CK is your carry out. This is the expression they have used. Your sum, that is SK equal to HK into CK minus 1 whole bar. This bar is there. Yeah, you can see this. Plus HK bar into CK minus 1. Here you can see this where HK is off sum. This is a notation they have given. HK is off sum, where HK is A bar into B plus A into B bar. As simple as, A XOR B. As a simple XOR gate. HK is nothing but your simple XOR gate. So when you come back to this sum expression, where sum is equal to HK. HK is nothing but your simple A XOR B. This is what I told you. This is A XOR B. This is XOR symbol. I've used different notation. A XOR B into CK minus 1 bar. This is the same CK minus 1 plus again HK bar is there. So here I forgot to mention this colon. This is AKA AXRB whole bar into CK. So in a way, I can write this one as simple as, AXRB XR CK minus 1. That is your sum. Your bar should come, while giving you notes, I'll include that. There is a mistake here. It should be, you can see HK area, and this is HK bar. This is X naught. So I should use dot. Yeah, circle I need to use X naught. Then carry is, as a simple carry. When you use this, K map and solve, so you'll get these two expressions, sum and carry. So your carry is, it's A XOR B into CK minus 1 plus A into B. In a way I can write AB plus HK into CK minus 1. Both are same. So I've just expanded these sum and carry equations. That's all. You can write directly this SK, this much you can write, and CK you can write, where HK is this. Just for our understanding purpose, I have given this equation. You don't have to write these equations. This for our purpose. Now, according to truth table, so I'm just skipping here. Everything I'll skip here. This is the same circuit. I'll come back to this this truth table. You can see from here. Last class, I hope you guys. I asked you to analyze this truth table and circuit. I hope you people have done it. I'll explain one more time since it is a little complicated because in the textbook directly is asking you to design full adder using mux. This is the uh, circuit, and you need to write only this truth table or the stick diagram. Multiplexer based add logic with the stored buffer sum output. This is the circuit diagram design. Again, directly if you see, it will be very difficult to understand this. So what you need to do is, from the truth table you need to understand. See here, this is, so first I'll go to this. If A is equal to B is equal to equal, if both are equal, take this one. So this is, here A and B are equal. Here also A and B are equal. Here A and B are equal. If both are equal, here A is 0, B is 0, then A is 1, B is 1. If both are equal, you see, your sum, whatever is there at the CK, can see this. Whatever is there at ck, it will go to your output. Correct. So this is your sum. You can see this. If both are equal, if a0 b0, whatever is there at the c in, that is ck minus 1, it will go to sk. Similarly here, a is 1, b is 1, a is 1, b is 1. If both are equal, whatever is there at the ck minus 1, it will go to output. This one expression. Then you see this. If both are not equal, take different pattern. If a and b are not equal, that is a0 b is 1, a0 b is 1, a is 1 b is 0, a is 1 b is 0. If both are not equal, whatever is there the carry in, whatever is there the carry in, it will go to this. Complement of that will go to output, right? Here ck minus 1 is 0, so here 1. If it is 1, 0, 0, 1. So to get your sum, if both are equal, whatever is there is the carry in, it will go to output, that is sk. If both are not equal, that is 0, 1. If it is there, whatever is there is the ck minus 1, complement of that will go to sum. Complement of that will go to sum. So same thing we need to write in equation. You can see this. You see this. That's what I have written in the equation. If a is equal to bk, that is a is equal to 0, then what is there at the sk will go to ck minus 1. If not equal, if ak is not equal to bk, then complement of ck minus 1 bar will go to sk. Complement of carry in will go to sum. So this should be very careful. Then similar way, like for carry, now we have learned about sum. Now I'll go to carry. If again, if a and b are equal, if a and b are equal, here in this case both are 0, then irrespective of your carry, what is happening is here both are equal, irrespective of your carry. You can see I've used this. So in this case, if both are equal, your carry will be either a or b. If a and b are equal, that is 0, 0. If it is 0, 0 is there, I can directly a will go to ck or b will go to ck, because both are 0. Same way, if it is 1, 1, if it is 1, 1, here also both are equal. Both are equal only. Only difference is here a and b are 0, 0. Here a and b are 1, 1. If both are equal, again you see here in this case a is 0, ak is 0. So you can assume ak is only going to output. You can take in other way also. Here b is 0, b also is going to ck. Other way it's same. So you can think in this way. If both are equal, that is a is 0, b is 0, whatever is there at the a, it will go to ck, or whatever is there at the b, it will go to ck. Similar way here in this case, both are 1. If both are 1 means, so again whatever is there at the a, whatever is there at the a, it is going to, it's going to ck. It is going to ck. It's going to ck. That is a, whatever is there at the a, it will go to ck. You can take whatever is there at the b also, it will go to ck. That is also fine. Then again, if both are not equal, imagine both are not equal. Yeah, a is equal to 0, b is equal to 1. Same color I'm using, so I'll change the different color. I'll go with this color. Yeah, in this case, both are A and B are not equal. If A and B are not equal, you can see what is happening. Whatever is there at the ck minus 1, whatever is there at ck minus 1, same thing is going to output, that is ck. Whatever is there at the input of ck minus 1, it will go to output. But in case of no, sum, it is complement of c in was going. Yeah, in this case, whatever is there at c in, it is going to output. This is a basic concept of your mux. So this way you need to analyze your this. Again, based on this concept, you need to write this equation. You can see if both are equal, if A and B are equal, whatever is there at the A or B, it will go to ck. Both are not equal, what is there at ck, it will go to output. So you can write your circle like this, you think in this way. Four combinations are there, so for four combination, you can see this is akbk. Akbk is nothing but both are 1 1. If both are 1 1, if both are 1 1, what is happening? Whatever is there at ck, it will go to sk. If 0 0, if it is 0 0 also, whatever is there at the ck, it will go to sk. This is a pass transistor, then 0 1, if it is 0 1, whatever is there at the ck minus 1 bar, it will go to output. Yes, someone can unmute and you can explain me, like whether you people are able to understand or not. You guys getting it? You can unmute and you can tell me.
Yes, sir.
If you're any doubt, say this one, like you can send message or chat. You can go to chat room and you can explain. If any doubt is there, you interrupt me and you can ask me. You can unmute yourself and you can ask me if any doubt is there. Because I won't be able to understand whether you people are understanding or not. If any doubt is there, you just unmute yourself and you can ask me. It'll be a
Okay,
little
sir.
difficult to understand. That's why I'm explaining one more time. Take your time, try to understand. If any doubt is there, you can unmute yourself and you can ask me. Okay, this is SK. Again, here also CK. To get the carry out, you need to use this one only. AKBK, that is 0 0 3 1 1 1 1. Directly I'm using pass transistor, is NMOS pass transistor. So where four combination will be there, 0 0 0 1 1 0 1 1. So here I'm taking 1 1 AKBK. If both are equal, so as per this timetable, both are equal. Here equal can be like either 0 0 or 1 1. See, these two are equal. We are also equal. If both are equal, whatever is there at the AK, I'm sending to CK. Whatever is there at the AK, I'm sending to CK. So you see, both are 1 1. If it is both are 1 1, whatever is there at the AK, it should go to CK. Same way, it is 0 0. If both are 0 0, whatever is there at the AK only, I'm sending to CK. I can take this instead of AK, I can make it as BK also. It works, right? So again, 0 1. If it is 0 1, what was there at CK minus 1, it will go to CK. Again, it's 1 0. What was there at CK minus 1, it will go to output. So if this condition, if both are not equal, what was there at the CK, it will go to CK. So these two are the circuit. But when you see in your textbook, what they have done is, in the textbook, they've used this multiplexer, that is n switches based added logic with the stored and buffered sum output. Buffered sum output means there will be a control signal called buffer just to delay your circuit data. So here is using one buffer. There's an inverter as a buffer. That's why in the textbook what he has done is, first he is taking directly, you'll get ck. This is ci is nothing but your ck output you'll get. But here over here is getting si bar. This is sk bar is getting as output. Then use using one transistor where gate is connected to clock. Through inverter is getting your si, that is sk output. So you need to think this way and you need to work. So your carry output is same. Your carry output you're getting as it is. You're getting as it is. But when you comes to sum, here is taking sum bar. The output is sum bar. Using clock and the inverter, that is using buffer, is getting sum. So directly you're getting Cout, but here, as per your textbook, here you'll be getting S bar. Then using buffer, you'll get this S. So based on the analysis, I have done this circuit. You can see, you need to think in this direction. This is a transistor, NMOS transistor. This is AI, BI. So both are 1 1. So I told you about this. I'll be explaining about this CK circuit. You see this, both are 1 1. A is 1, B is 1, then A is 0, B is 0. In both the cases, AK is coming as an output, right? AK is coming as an output. So if A is 0, B is 0, your CK is AK only. Again, if A is 1, B is 1, A is 1, B is 1, whatever is there in the AK, same thing it is going to CK, right? So as per that, what I have done is I've used this transistor. You see this is the gate. Gate is connected to AI. Again here, gate is connected to BI. These two transistor, AI, BI. So directly I can take 1 1, 1 1 combination. If both are 1 1, whatever is there at the A, you see in this source is shorted to, can I draw this? Source is shorted to AI. This is very important. Source is shorted to AI. If A is 1, B is 1, whatever is there at the AI, this is metal layer. This is blue color I'll take. You need to think this direction. This is blue color is your metal. This is metal. Thin line is your metal. Thin line is your metal. This gate is connected to AI. Gate is connected to AI, and BI is also connected here. This is transistor polysilicon, the gate. So source is connected to AI here. Source is shorted here. Then A is 1, B is 1, whatever is there at the AI, it is going to through this. This is source, this is drain. You see drain shorted. So there is no contact. So directly it will go to output. That is CK will be your AI. When both are 1 1, AI will go to CK. Similar way, we need to think this way. You see here also this is shorted. I have shorted this. So this is 0, that is A bar. A bar is connected here. A bar and B bar. A bar and B bar, these two are shorted. When 0 0, if 0 0 means these two transistors will turn on, then whatever is there at the source, which is shorted to AI, will go to CK. Will go to CK. This is 1 1, then this is 0 0. For 0 1 combination, you see, if I go to 0 1 combination, for 0 1, what is that? For 0 1, that is 0 1 1 0. For A and not equal to B, whatever is there the CK minus 1, it will go to CK, right? So you see, this is A bar. This is A bar. This is A bar transistor, and this is B transistor. A bar, B. This is 0 1. If 0 1 is there, whatever is there at CK, you can see this. This is CK. From here, Ci minus 1. That is Ci minus 1. It is coming this way. See, Ci minus 1. It will go this direction to output. So A bar B. Clear? This is A bar B. Same way, this is A B bar. A B bar also CK will come to output. Clear? Then here, what you have done is these things. Similar way, for some here you can see this. I've used this SK bar. So you need to think in this direction. The output here is, according to your textbook, this is SK bar. So same way I've taken. So if it is, this is A bar, this is A bar. You can take this. This is A bar, is connected to this, and this is B. That is 0, 1, 1, 0. Sorry, 0. This is 0, and this is 1. If it is 0, 1 is there, you see, your SK will be CI bar, but actually since I am taking this SK bar, you should be careful. So what is happening, if you take this circuit, you see this 0, 1. This is your 0, 1. If it is 0, 1 is there, CK bar is going to sum. But as per this circuit, as per this circuit, CK only is going to output. You see, the CI is going like this. So that's why you should be a little careful, because we are taking complemented of sum. We're not directly taking sum, so we're taking complement of sum. So again, you see this A. You can take this. This is what? This is A, and this is B bar. A B bar. So again, A B bar. When you take sum, it's CI bar, but SK bar is there. So that's why you're getting this sum. So directly CI is going through this transistor. Again, if you take this transistor, this is transistor A and B, AB. If it is AB, actually it is CK, but here you're getting CI minus 1 bar. So this is CI minus 1. So inverter is there. You'll be getting complement of that. And this way your SK bar will be this. So that's what you need to see. Like you need to make sure, according to textbook. If you want directly, as per your sum and carry, you can take this one only. But since it is this one, so we'll be using complemented output. So you need to analyze this circuit. Based on the circuit, you need to draw your sum and carry. So any doubt is there in this? You can unmute and you can ask me. Any doubt? Many a times, they'll be asking this adder using mux. Many times we have different adders. This is one of the major, like added element using mux, where obviously when you use pass transistor, number of transistor will come down compared to your CMOS and different other logic structures. So, and delay will be very less, and number of transistors required to implement also will be less. We have this drawback now where the threshold voltage will be very less. But when you talk about digital, since VTH will be high, we won't be that much effect won't be there. Obviously there'll be a signal degradation when you use this NMOS transistor. That's why we'll go for this transmission gate. But when you actually implement it, if you implement any logic circuit using pass transistor, you won't get in cadence tools. We have done this exercise. Your seniors have worked on this pass transistor, but they're getting proper output. So I don't think so there'll be a problem, right? So this is the same circuit, like now I have drawn stick diagram with respect to this. You can see this. What I have done is no. So you try to analyze this. What I have done is this is how I have drawn stick diagram. So here you see, I told you about this pass transistor where gate is connected to AI and source is also connected to AI, because when both one AI should be shorted. If you miss out this, your entire logic will be wrong. So you need to make sure this AI is shorted. Again, you see this is how I've done my stick diagram. This shaded line is your I'll zoom in. You see this? Let me zoom in a little bit. See how I done it. This is your polysilicon. So I have taken this way. This is your polysilicon. Polysilicon, it is connected to your AI. That is metal. This thin line is metal, and this is source, and this is drain. Like that I have taken. This is source. This is not proper. This is source, and this is drain. That's what I have done. Source also is shorted to AI. Source also is shorted to AI. So you need to be careful in this. If you miss out this connection, your entire circuit will be wrong. So that's what I have done. You see this carefully. This is the stick diagram I have drawn. But if you go to actual this circuit, what is there in your stick diagram, it looks like this. You can see this. I'll zoom in. This is there in your textbook. You can see this. We've done it in other direction. That's all. So this is your polysilicon. This shaded line is polysilicon, where polysilicon is shorted to again AI. And there is a contact. There's a contact. Take different color. You can see this. There's a contact here. This acts as a source, and this acts as a drain. The blank line is your diffusion. This is diffusion, and this is gate. This is gate. Understood? Any doubt in this? Guys, can anyone respond me? If you can unmute and you can tell me. Please. Is any doubt? Is any doubt? Need to respond. Then only I'll understand whether we're talking about
Yes,
this.
sir.
Understood?
Yes, sir.
Okay. I can hear only your voice. No one is responding. Okay. Again, I've done in opposite direction, but it doesn't make any difference. Like this polysilicon is connected in right hand side, I have connected in left hand side. That's all the difference, and the rest of things will remain same. So this is how you need to do. Carefully you try to understand and do it. Last class also I discussed about this, because last class when I started, so I didn't know, whether you people have understood or not. What are the feedback I got? I went a little fast, it seems. That's why I'm going a little slow. Last class also till there I've completed. Now come back to this one. This is generally they will ask, implement adder using pass transistor. Implement adder using pass transistor means you need to draw only this circuit. You don't have to write this circuit diagram. This is not required. This is not at all required. Only for our analysis I have done it. Only directly you can write the stick diagram. This will be sufficient. Only thing is you need to take this truth table. You need to explain this truth table with this equations. This truth table and this equations, if you write, that will be more than sufficient. Again, these circuits are not required. This is for our understanding. Only you require this stick diagram. Again, they can ask this also. Implement adder using mux. Implement adder using mux. That case also you can use this, because you can see, many inputs are there, and using select line you can do it. Adder using mux or pass transistor. Here in this case, control signal will be your this scene. That way you can take. Okay, come back to this next topic, that is, ALU. ALU, implementation of ALU function with the adder element. Again, no, because when you take adder, you can use adder to implement many functionality. Using adder, you can implement a subtractor, and you can do normal addition. At the same time, now you can shift your data. This is, like you can use the same adder to implement all the logical operation, including or and XOR, every operation you can do. So that's why now we'll be using this. Now this is implementation of ALU function with an adder element. Yeah, you can see this. Normally you can do addition, and you can do subtraction also. How you can do subtraction? If you want to do this a minus b, what you will be doing is, you like a complement of second bit, that is b bar, then you add this a plus b bar, so you'll get subtraction, right? This is simple subtraction. Already you know about this thing. In addition to this, that is addition and subtraction, you can do logical operations also. You can do logical operations. So how you can do it? Using these equations. Again, same equation. The sum is this hk into ck minus 1 bar plus hk bar into ck minus 1. The same equation, whatever equation I have given in the previously, same thing I have taken. So this is your sum, a XOR b into ck minus 1 plus, again as I told you, there will be a complement. This is a XOR b complement into ck. So finally it's a XOR b XOR ck. Then ck is a into b plus hk into ck minus 1. Again, if you use your truth table, you'll get this equation. So this is a XOR b into ck plus ab. This is the equation we'll be getting for carry. And for sum is a XOR b XOR ck, or I can write this way: a XOR b into ck bar plus a XOR b whole bar into ck. Either way it's correct. Here there will be a complement. There will be a complement. So complement I can take it this way. So there is a complement here. There is a complement. So now what we are doing is, now you take the sum equation. In a sum equation, if I make ck minus 1 0, see this, if in a sum sk, if ck is held at logic 0, then what will happen? No, in the sum expression, if I make the ck minus 1 is 0, this is 0, this is ck minus 1 bar is there, so it will become 1. This is 0, obviously, complement of that will be 1, so that will be hk into 1 plus hk bar, correct? So what is hk? Hk is nothing but your a XOR b, right? So your hk is a XOR b, right? If you take this a XOR b, directly you can implement XOR function. So if I, in some expression, if we make ck minus 1 is equal to 0, you will get XOR operation. Same way, if you make ck minus 1 is equal to logic 1 in some expression, so again what will happen? If I make sum is equal to ck is equal to 1, this is 1, so this will be 0. So 0 into hk is 0 plus hk bar into ck. So what will happen? So this expression will be hk into 0 plus hk bar into 1. So this is your XNOR operation, correct? This is your simple XNOR operation. Same way, in ck equation, if ck equation, in ck, if ck minus 1 is held at logic 0, ck is hk into ck minus 1 plus ab. If I, in this equation, that is ck is a into b plus hk into ck minus 1, in this, if I make ck minus 1 is 0, if I make ck minus 1 is 0, hk into 0 will be 0, so I'll be left with ab. AB is nothing but is a simple and operation, right? Hk into 0, so this everything will be 0. I'll be left with ak. This is just control in an equation, in a circuit diagram of sum and carry. You need to control your carry. Based on your carry, you can get all your logical operation. Same way, if I make logic 1 ck minus 1 is logic 1, you will get or operation, right? So a into b plus hk into 1, to simplify this, you'll get a plus b or bk plus ak. This is or operation, right? Understood this? This is very important. This question also many times they've asked, implement ALU function. Explain with an expression how you implement ALU function with an adder elements. Means no, you need to write this things. ALU you can use for addition as well as subtraction. Subtraction you can do this way. In addition to addition and subtraction, you can get all your logical operation using these expressions. So you need to write all this expression. If I make ck minus 1 is equal to 0, I'll get XOR gate, XNOR gate, then and or all the operation you can get. If you take complement of that, other gates also you can implement. This is all you need to do. And in addition to that, you need to write this circuit diagram. You need to remember and you need to write this circuit diagram. Generally, they'll ask, implement ALU using full adder, they'll write, or 3-bit implement 4-bit ALU using full adder. In that case, you need to write 4 full adders. You need to write complete 4 full adders. If they ask 3-bit full adders, 3-bit ALU, you need to write this. So you should be careful. You should be careful while designing this. If it is for 3-bit, you need to write this 3 blocks you need to use. There's nothing is there, only this circuit. Here he is telling how you can take A naught and B naught, B naught bar. So that much only is there. You need to remember this circuit. You need to write this exact same circuit. If it is for 3-bit, you need to write 3 blocks. If it is for 4-bit, you need to write 4-bit. If it is for 5-bit ALU, you need to write 5 blocks. Understood? Any doubt is there, guys?
No, sir.
Okay.
Sir,
Yes.
how are the connections made over there with the equations only, sir?
No. This is nowhere related to equation. Only this connections are there. That's all. That's why I told you need to remember this
Sir,
circuit.
then connections we should remember, sir. Then
Yeah, nothing to remember. Just write similar to this structure. That's all. There's no connection
okay,
here.
sir.
You can see this. There is a VDD is passing to all the added element. There is a ground. Carry signal is coming from carry in will come here. You can take A naught. Here you'll be taking
Okay,
either
sir.
directly B or B bar like that. Just a connection. That's all. Nothing else.
Okay, sir.
Again, based on your requirement. If they're asking 5-bit ALU, you need to write 5 blocks. If it is 3-bit, you need to write 3 blocks only, and you need to write this circuit diagram. You should not miss out. After writing all this equation, you need to write this block diagram. This is very important. Generally for this
Okay, sir.
circuit only, or this diagram only, they'll give 2 marks or 3 marks separately. They'll include in our scheme actually. Okay guys,
Yes,
like
sir.
uh, just go through again one more time this adder. Try to understand. If any doubt is there, again yes, someone can add me in your WhatsApp group. If any doubts is there, you can ask me in WhatsApp also. I'm not able to communicate with you people. So if any doubt is there, you can ask me, or you can send me message also. So that one also you can do it. Just go through it, and
Okay, sir.
next class we'll discuss about this uh, pass and generate carry concept. Yes, yeah. Thank you. Thanks a lot.